been a while. I think you know what time it is. This is the 2.8 quizzes for stats. I do not know why this is still on, but whatever. So this is assessing regression models. Okay, so as it says, the residual is the actual y value, so the measured y value, minus the predicted y value by the regression line. So on this one, the regression line is y hat equals 113.6 minus 0.921x. So the x is the height of the person, and the y is the number of steps that they take to walk the length of a hallway. So calculating the residual for a person who's 63 inches tall means that we plug in 63 for our x. So y equals 113.6 minus 0.921x. Our line looks something like this. So if we find our point 63, that means we have 55.9. So that's our predicted value. So it wanted us to find the residual. So the residual is actual minus predicted. So then it gives us an actual value of 59. So that means it is 59 minus that, which is 3.423. So bad residual plots are ones that have a pattern to them. So this means that this blue one, you can see kind of has a quadratic or a exponential look to it, meaning that the fit was that with the regression line that was given for it was not good, because the residuals still have a pattern. If the residuals have a pattern, that means there's something wrong with the regression line. This one, it kind of has a pattern as it slowly gets more and more varied as it goes on, but generally this looks kind of random, but there is still the pattern of it getting more varied as it goes on. So a good regression line or a good residual plot is one that is completely random and sticks close to zero. What a linear regression model. Okay, so this would not be appropriate because even though the residual pattern is semi-random, you can still see that it forms kind of a quadratic shape like this. And the variance is super high. It is not close to zero. You have upwards of 15. You have stuff that negative 15. So no, it is not good. This residual plot shows a regression model that is good because all of the dots are fairly close to zero and there's no pattern. That are all randomly distributed. So yes, it's good. What should a residual plot look like? It should be random, as I've said. Coefficient of determination. This one's a bit tricky. This one took me a little bit. So r squared, the r value is the correlation coefficient.
It's the Mahajapit, Majahapit, Mapajahit, Mahapajit, Mapajahit, Majapahit.
So r squared is the coefficient of determination. So I'll just read this off. Roller coasters with larger heights usually go faster than shorter ones. Here's a least squares regression line for 9 roller coasters. Okay, so that's the least squares regression line where x is the height and y is max speed. Okay, cool. So its r squared is 0.887, which is a percentage number of 88.7%. To get the percentage number, you just multiply this by 100. So this means that 88% of the variability in roller coaster maximum speed is accounted for by the model, where x equals the height in feet and y is the maximum speed. Or like, this model is correct within 88% or so. Okay, so this question, which is the correct interpretation of the coefficient of determination. Well, there's only one of these answers that actually has a coefficient of determination, and it's this one. So it's that 34.2%, which matches that r squared value right there. But looking at this one, 34.2% of the variability in the battery life is explained by the least squares regression line with x equals price in dollars. That is the correct answer. You can tell because, again, there's this percentage matches the r value, and because of the description of this. This is the definition of an r squared value. Some percent of the variability in something is explained by the least squares regression line with relation. Standard deviation of residuals. So this is pretty close to just standard deviation in general. So its interpretation is the actual value is typically some number away from the amount predicted by the least squares regression line. So rather than how far they are from the mean, it's how far they are away from the regression line. So that means the roller coaster's larger heights usually go faster. So that means the actual maximum speed of a roller coaster is typically 10.5 miles per hour away from the maximum speed predicted by the model. So it's not talking about means here, it's talking about the regression model. So think of this as the standard deviation for a regression line instead of the standard deviation for a mean, which is the correct interpretation of the standard deviation of the residuals. So that would be this one, because that's, again, the only one that actually includes the number in it. But the actual battery life in hours is typically 1.21 hours away from the predicted by the least squares regression line. So this is the actual something is typically something away from the predicted value by the least squares regression line. That is what, again, it's standard deviation. No, don't use my microphone. Thank you. So again, it is standard deviation, but for regression lines. So this would be interpret standard deviation of the residuals. Okay. The measured values of number of hurricanes Y typically vary from the regression line by 3.2 hurricanes. So hopefully this makes sense as to why that is correct. Interpret the coefficient of determination. Okay, so interpreting the coefficient of determination is relatively easy. So if it's low, like 0.15, that means there is a low correlation between the years after 1950 and the number of hurricanes, because the coefficient of determination is 0.15. So the lower the coefficient of determination, that also means the lower the R value. So the lower the coefficient of determination means that the lower amount of percent of variance can be accounted for by the model. So this means that only 15% of the variance in number of hurricanes can be explained by the least squares regression line. Next. Hopefully that makes sense. Yeah. How to determine if a model is appropriate. Residual plot shows no pattern and the stuff is close to zero. The small standard deviation of the residuals, that means everything is relatively close to the regression line. Large coefficient of determination. You want that number like high, really, really high. Okay, so this outlier right here has really low leverage because it is near the center of the data set or near the mean of the data set. It has some influence because it has a really, really high residual. So if you removed it, then the y-intercept, as you can see from this line here, would go down, not a hugely significant amount, but a decently significant amount. Okay, so this is, I don't know what all this other crap is on here, but whatever. We roll on, we continue. Outlier number 2 down here is high leverage because it is far away from the mean x value of the data set, and is high influence because it has a high residual value from the line. So removing it will cause the line, the regression line, to change y-intercepts, slopes, or possibly correlation coefficients. Generally, something high influence doesn't have to have a high residual, but usually it does. So like here, if I pulled up paint and I draw out something like, here we have our graph, and we have a bunch of little plots. So what right now we would say this regression line probably looks something like that. But if we added an outlier over here, the new line would probably look something like that. Now, this does not have a very high residual, but if we remove it, the regression line changes to that. So this is a high leverage and high influence point. It is high leverage because it is far away from the center or the mean of the x values of the data set. And then it is high influence because when removed, it changes how the line looks. Okay, just went over all that. Okay, so outliers, really easy. They seem complicated, but they are easy. So, using the IQR rule, or the interquartile range rule, of 1.5 times the IQR. The IQR is the distance between quarter 1 and quarter 2. So, let's say that quarter 1 was 3. I don't know what we're measuring or whatever, but quarter 1 was 3. Quarter 3 was 8. That means our IQR is 5. 8 minus 3. It's the distance between those two. So that means our rule for outliers would be 1.5 times that. So 1.5 times 5 is 7.5. So then we apply quarter 1 minus 1.5 times our IQR, and quarter 3 plus 1.5 times the IQR. Anything outside of that range is considered an outlier. So in that data set, if we had something that was, let's say, 20, and we know that our IQR rule says that anything 7.5 times or 7.5 plus Q3, which Q3 was 8, is an outlier. So it'd be 8 plus 7.5, which is 15.5. 15.5 is less than 20, meaning that 20 is an outlier. Yeah, okay, did all that. Did that. Nope. Okay. Transformations are pretty easy. I'll show you an example of one. So all of these are just functions that you apply to another function. So if you have let's see. If you have a okay, these make sense. So if you have a y equals a to the bx, then you would take the log of the y value. So here, I'll show you how this works. So if you have like y equals 2 to the x. Yeah, there we go. So to undo it, you take the inverse function. So see, we start with this function, and then we take its inverse, which is the log base 2, since this is our base of 2. Then we get this nice straight line, which is now linearized. Defines a high leverage point. A high leverage point is one that has a extreme predictor in the x value, yes. So a high leverage point. High leverage and high influence are relatively the same thing, as if you remove or add a high leverage point, they will almost always change the effect, or they will usually change the slope or the y-intercept, and it is usually a point that is an outlier, but they do not have anything to do with the y. Example 1, why are there no influence? Okay, this question, I don't really know what it's talking about, but why are there no influential points? Generally, if there's no influential points, that means everything fits the trend or the regression line. So all points have high leverage? No. All data points are outliers. If everything is an outlier, then they're all influential points. All data points have a high R2 value. Not necessarily. It would generally be this one. All data points follow the general trend and none are extreme with respect to the X. Okay. This one kind of sucks because it's really, really small. Oh, and I can't zoom in on it. No. Can I? Yay, I can. Okay, so 2 variables. Model A looks like it has a pattern, which means that it is not fit correctly. Model B has no pattern, or looks like it has no pattern, and they're all relatively close to 0. This means that it is the better fit. So, if you'll take a look at this again, response is log y. Response is log x. So that means model B is appropriate since the relationship between x and log y, which is the response is log y, is linear. And it was linear because there was not any high residuals. Okay, a linear regression based on this residual plot, which is the following. Okay, 1. The relationship between tuition cost and the year is not linear. Based on this, we can tell that if a linear fit was given, yes, linear regression line. So since the linear fit was given and there's still this quadratic pattern remaining, that means that it is not a linear relationship. So far, 1 is true. Oh, I forgot about that. Hold on, let me go back and explain the rest. Number 2, tuition cost decreased from 76 through 1982. Okay, the curve or the slope of this line has nothing to do with the actual tuition numbers. These are just the residuals. This regression equation would underestimate tuition cost in 1992. That is not true because a negative residual means that the regression line overestimated. Because if you have a negative residual, that means your actual data value was underneath the predicted data value. Okay. Scatter plot shows which of the following conclusions can be drawn from this information. Okay. Square root function, no. Exponential function, no. I don't remember this one. Hold on. I think it's power function. No, it's not. It's exponential function. Okay. Cool. We'll skip that one. I'll edit that one out. Okay. So, what is the effect on the graph of the linear parent function f of x equals x when f of x is replaced by f of x minus 7. So this is just like basic algebra 1 transformations. So the graph of the line shifts horizontally to the right. Because, here, let me go back to Desmos. If we have f of x equals x, and then f of x minus 7, you can see that when the value is inside of the x, I like to call it the determinant. I don't think that's what it's actually called. But when it's inside with the x variable, it moves it horizontally. And when it is negative, it shifts it to the right. And when it is positive, it shifts it to the left. Okay, so f of x minus 6, f of x minus 6, it has now been shifted downward. Actually, I need to get like a better function for this. F of x squared. There we go. So we can now see that it has been shifted downwards 6. As you can tell, it's little, I don't know, 0 point, instead of 0, 0, is now 0, negative 6. So that means it is shifted down 6 units. Scatter plot, hold on, use shift forward. For straightening a curved, oh yeah. So that is taking the logarithm of one or both variables when a power model describes. So when using power models, take logarithms, logs, 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 because logarithms and powers are inverses of each other. Curved relationships between two quantitative variables can sometimes be changed into linear relationships by transforming one or both of the variables. So that was doing what we did earlier with the +7, -7, -6, and then also taking logarithms of stuff. So applying a function, or applying a operation, I should say, to a regression line or a function will transform it in some way. I believe that is it. Hope everybody has a good rest of the week. Depending on when you're watching this, I don't know if it's the end of the week or not, whatever. And I'm always here. I guess I'm starting making videos again. Hope everybody has a great year.